Hello, I'm Vincent Roykers. This is Lab 4, Oscillations. In this lab, we are tasked with using Newton's second law to track the position and velocity of an object oscillating on a spring in the x and y directions. Some components of Newton's second law that we used here is that the net force is equal to the sum of forces acting on an object. In this case, it was gravitational force and spring force. We also used that the net force is also equal to the object's mass times its acceleration. This was used to update the object's velocity, and also with this we could also update the object's position. We also examined the relationship between kinetic energy, spring potential energy, and gravitational potential energy. We will see later in our results what the relationship between these are, but for now we also used the spring's period to predict its spring constant. Well, I didn't actually calculate this for ourselves. According to TA, we could just use the spring's constant from the video. If I were to calculate... Okay, so let's look at our tracker footage. What's important to notice here is that we set the origin to be where the spring is attached to. And we have it going vertically down, so we can track the x direction motion, the y direction motion. So now let's observe the tracker motion. As we can see here, the x motion oscillates, and if we looked at the y direction, we'd also see it oscillates between 2 points too. So now let's look at our model after importing this as a CSV file. So here's our computer model. Some important things to notice here is 9.8, the gravitational constant. For the spring's constant and the rax length of the spring, these were given to us in the video. Our TA told us to use these. So for the length vector, this is just the ball's position minus the origin of the spring. And then to get the direction, we can just use the normal function for this vector. And then we use this vector to calculate the stretch of the spring, and this is just how long the spring currently is minus its relaxed length. We then calculate the initial energies. So here we just store them because they're used later to calculate the changes in them. For kinetic, it's just 1/2 times the ball's mass times the ball's velocity squared. For the potential, gravitational energy, it's just the ball's mass times the gravitational constant, which we predefined, times the ball's y position. For the potential spring energy, this is just 1/2 times the spring's constant times the stretch squared. And then for the total energy, we just add these together. So going into our calculation loop, it's important to save all these energies as an initial because we'll be changing them later and we need to find the change in them. So first we need to define our spring's position updating calculations. So here we need to it's important to calculate the gravitational force, the spring force, so we can calculate the net force, and we use the net force to then update the ball's velocity. And because we're using a small enough time step, we can then update the ball's position with just velocity. We then update the length or the length vector. Again, using pretty much the same calculations before, actually the exactly same calculations before. And then we update the energies and we find the changes in them using what we've saved earlier. These are again just the same calculations as we've done before. And then pretty much that's all that we've changed in this loop. Now let's watch it run. So here we can see the gravitational force and the spring force. The spring force is strongest when it's furthest away from the origin, and we can see it gets weaker as it moves closer, and the object's oscillating. Pretty much does this for a while. We can just look at the final results in my PowerPoint. So here is our computational results. Here we see that the spring's potential energy often peaks while the gravitational potential energy is at its lowest point, and we see that as they oscillate, they are opposites of each other. And another important thing to distinguish is that the total energy change is approximately 0 the entire time. This is important for a question later. So here are our results. Here we can see that that our the observed motion isn't exactly the same as our computational one, as there might be small losses of energy in the system. So going on to the questions, the energy principle, at least for our model, and maybe even our observation, is satisfied as the total change in energy is approximately 0, showing no input or output from the surroundings. So going into whether we should use the period of the y direction or the x direction, um, going back to the tracker data, we see, or we at least know that we had more periods of oscillation with the y direction. So at least in that point, I'd feel that the y direction would be more accurate than the x direction. And for how they calculated the spring constant earlier, the y direction would be closer to how they calculated their original spring constant, and I would use that in my calculation of spring constant if I had to do that.